right, welcome back after the last video. So the idea or the example of when I was holding my keys and I said that the keys were what applying a force to my hand via the tension. So in this case, what I know is that my keys again have a mass to it. That mass then is pulling downward gravitational force. So in this case, it has to feel a tension upward, but simultaneously the tension is acting downward on my fingers, which means for me to hold these keys up, I'm being applied downward on force due to the presence of the keys via the tension here. So my tension is acting as an intermediate, and then that's pulling my hand down. So my hand has to apply a force upward to keep this guy static or stationary. So this brings up the idea of what we call Newton's third law. So Newton's third law says is that for every force that is applied, there's an equal and opposite force. So, or an equal opposite reaction. So what does that mean? So that means that anytime two objects are applying a force to each other, or they're pressing up against each other, then one object is applying a force to the first object, but then the second object applies a force then onto the other object. So what do I mean by that? So I mean, if I was at the grocery store, or in this case, I'm going to push my chair. So for me to push the chair across the room here, I have to apply a force to the chair. However, simultaneously, the chair is applying a force back onto me, and I can feel that because as I push it, I can feel two things: the weight or the resistance or the inertia of the chair as I'm trying to push it across, and once it stays stationary. And then the other thing is what? Because of the friction on the floor, and we'll talk about friction just a little bit. So this is what we call Newton's third law. Newton's third law says is that for every force that's being applied between two or more objects, there's an equal force which is pushing back onto the other objects. So let's draw that. So Newton's third law again simply says that if I have two objects, so here's my first object, let's say me pushing on then another object, which let's say is another person. So this is object number one, this is then object number two. So in this case, what this then is that object one will push onto object two. So in this case, I'm pushing onto this guy in this direction. This is going to be the force on 2 by 1. So the way I read this is the first position that shows up here, which in this case is 2, is talking about the object that I'm speaking about, which in this case is object number 2. And then the 1 in this case is talking about where the force is actually coming from. So the way I read this then is that this is the force on 2 by 1. However, what we know is that this guy then is going to feel a force in this direction, which is going to be the force on 1 by 2. So what Newton's third law says is that these two forces are equal and opposite. So if I wrote this out as a force, what this says then is that the force on 1 by 2 is exactly equal to the force on 2 by 1, just in the opposite directions. Now, this is true not only for direct contact like we're looking at here, but it's also true for long distance forces as well. Where for a long distance force, the force then would be along the line that connects the two objects here. So in this case, I would have equal and opposite forces on each one of these guys as well. But the direction of the force would be along the line that connects the center of these guys, which would be this line here. So this is Newton's third law. So Newton's third law says, again, that the magnitude of these two forces are then exactly the same, but again, the directions are just completely opposite from each other. Now, again, in this case, I'm considering, say, me pushing onto somebody else, or this can also be me pushing onto a shopping cart. So your shopping carts, wheels. Right, so in this case, I'm applying a force. So this is then force on the cart by me, but simultaneously, the cart is putting a force onto me. This is the force on me by the cart. Where again, that these two guys are equal and opposite. Now, this is also true, for example, when I lean against the wall. Okay. So in this case, when I lean against the wall, I'm applying a force to the wall. But the reason I'm not falling in this direction due to the fact that I'm leaning is because the wall is applying a force back onto me by Newton's third law. Okay. Now, this is Newton's third law. So Newton's third law again simply says that for every force, there's an equal and opposite force. So this is Newton's third law. So for every force, there is equal and opposites. Now I can't spell the opposite force. Newton's third law. So this will always be true. So anytime I have two or more objects interacting with each other, one's going to apply a force onto the first one, but then that first one will apply a force then onto the second one. But again, the magnitude of those two forces will be identically the same, but the directions of the forces will just be opposite from each other, no matter how it is that I'm pushing. Now, why do we care about this? Well, basically, we care about this for multiple reasons. So let's say I have objects which are connected to each other. Okay? So let's say, for example, I have, I don't know, an inclined plane. So here's my inclined plane. And then at the end of it, let's put a pulley here. So I'm going to hang a mass on this side. Let's go to this guy M2. And then here, I'm going to draw a mass M1. And then these guys are going to be connected by a string. Okay? Now, if I look at these guys, then here I'm going to have what? Some acceleration on this guy. Let's call that guy A2. And then this guy's going to be accelerating down in this direction. Let's call that guy A1. And then what I know is that what this guy here is going to feel a tension. So this guy's going to have a tension force pulling up on it this way. And let's call that T2. And then this guy here is going to have a tension pulling on it in this direction. Let's call that guy T1. Okay? Now, what Newton's third law again says is that what? The force on each one of these two objects are equal and opposite. Now, in this case, what does that mean? What this means then is that the tension T1 then has to be completely equal and opposite to the tension T2. This is what Newton's third law is actually telling me. Now, when it comes to Newton's third law, we have to be a little bit careful in the fact that when I'm writing out Newton's third law, or at least Newton's second law, to use Newton's third law, we only look at one object at a time, right? Which basically means in this case, the reason that M1 is accelerating with the acceleration it has is because it's being pulled by the tension, but the tension in this case is being supplied by the fact that M2 is accelerating downward. Now, I'm not going to ever look at M1 and M2 together in the same expression. I'm going to look at M1 separately than what I'm going to look at for M2. Now, what does that mean? What that means then is that M1 doesn't necessarily know directly about M2, and M2 doesn't necessarily know directly about M1. But what M1 knows is that it has a tension T. M2 also has the same tension T, so M2 will learn about M1 via the tension T, and M1 will learn about M2 via the tension T. So in this case, the tension acts as the mediator between the two masses, but each of the two masses don't necessarily have to know what is actually pulling them. All it knows is that they're being actually pulled. Now, let's go back to Newton's third law. So in this case, what Newton's third law ultimately tells me then is that the tensions T1 and tensions T2 must be equal and opposite to each other, right? Now, again, this is only true if this is massless and frictionless. If this is no longer massless and frictionless, then that is not a true statement anymore. It's going to be related to each other by how the pulley is actually rotating. But again, we'll talk more about that as chapters progress. But in this case, what this tells me then is that what? Again, the two tensions have to be the same. Now, since these two tensions have to be the same, what that ultimately then fixes is that what? For our purposes, Newton's third law then tells us that these two accelerations then also have to be identically the same. So the fact that these two tensions are the same tells us then that A1 is actually equal to A2, which we're just going to write as some acceleration of A. So for our purposes, what we can imagine then is that Newton's third law basically just tells us that the accelerations of these connected objects is then the same. Right? So this is going to be true for any connected objects. So again, for connected objects, what the third law implies then is that the accelerations must all be the same. Now, this will be true regardless if the pulley could actually rotate with mass and friction. Right? So that would actually be true as well. But in this case, the thing that Newton's third law gives us is that the two tensions are the same, which means that the two accelerations must be the same as well. Now, again, this is only true, at least T1 is equal to negative T2, if, again, that this thing is massless and frictionless. But in the case where it is massive and friction full, in that case, the acceleration still being the same is exactly true based off of Newton's third law. So ultimately, what Newton's third law just ensures to us is that the accelerations of all the objects which are connected to each other are going to all be the same. So we can then use that to then determine, say, the acceleration of our system. So let's actually look at the system that I drew. Let's say that this thing is tilted at theta, and then see how we would actually solve this using Newton's second law. So as I said, what we have to be careful of is when we use Newton's second law, we can only look at one object at a time, which means I can't look at M1 and M2 together as an entire whole. I have to look at them separately as two separate objects. So that means then is I'm going to draw my free body diagram for each of the two objects. I'm going to have one for M1, and then I'm going to have one for M2. Now in this case, let's go ahead then and draw our free body diagram. So let's label all of our forces. So let's start off with M1. So M1 we know has a mass, therefore it has to have a gravitational weight. So it's going to have an M1G. Now, Mg, or the weight, will always be straight down, regardless if it's on an incline or not. So meaning in this case, my box here is on a flat surface. So in this case, we know Mg is pointing straight down, normal force is going to be straight up. But when I rotate it now, we know a normal force is going to tilt, because it's always going to be perpendicular to the surface, as we talked about in the previous video. However, the weights will always still be straight down. So no matter how I rotate this thing, whatever extreme angle I put it at, my weight will always be straight down. Now, in this case, again, we know our normal force is going to be perpendicular to the surface. So this is my normal force. Here, we're then going to have a tension. Let's go ahead and draw my tension. I did green last time, so let's do green. So this is my tension, T. We also know this thing has an acceleration. Now, the acceleration, also be careful, is not a vector, or sorry, not a vector, it is a vector. It is not a force. So in this case, when you saw me draw on a free body diagram, I'm always going to draw it off to the side just so I know what direction the acceleration is, just so I'm consistent in choosing the direction of my coordinate systems. But just note, it is not a force, it's the result of a force. One thing I should mention that I didn't mention last time is what Newton's second law says, again, is that the sum of the forces is equal to the mass times the acceleration. Since mass here is always a positive quantity, this thing is always greater than 0. What that means then is that what? The acceleration will always point in the direction of the net force. So when net force points in this direction, then my acceleration has to point in the direction of the net force. That's what Newton's second law tells me. Because again, the mass is a positive quantity. So since it's a positive quantity, it has to point in the same direction as the net force, as we talked about in the vectors chapter. So good. So we haven't talked about friction yet, so we can ignore friction. So basically, those are all the forces on this guy. So now let's look at M2. So M2 is going to have, again, weight downward. So I'm going to get an M2G downward. And then I have tension. In this case, tension is going to be pulling upward on it. So this is my tension. But we know this guy is going to be accelerating downward with the same acceleration A. Right. So these are my free body diagrams. So now what I want to do is look at each individual free body diagram and then use that to solve for the overall acceleration. So let's say ultimately what I want to know is what's the acceleration of my system. Now, again, when I write out Newton's second law, I'm only going to look at one mass at a time. So initially I'm going to look at only say M1, and then I'm going to look at M2, where I'm not going to make direct reference of M2 or M1 and vice versa. But again, what's going to tell M1 about M2 is the tension. And what's going to tell M2 about M1 is the tension. So again, what's going to mediate the information about the two masses to each other is the fact that the tension exists. So I'm going to use the fact that the two tensions are the same at some point once I write everything out. But in the beginning, I'm just going to leave everything in terms of the tension and then eventually use the fact that Newton's third law implies to me that these two tensions are the same. So let me quickly redraw these over here on this page so we can write out Newton's second law for each one. So here's M1, and then I have M1G down in this direction. There we go. G, normal force, this direction, normal force. And then we have our tension down in this direction. So here's that tension, the rate, and then up here, let's draw M2. Good. So again, M2G downward, and then we have our tension upward. I'm going to draw my acceleration, so I know acceleration is going to be in this direction. For this one, acceleration is going to be this way. Great. So now let's apply Newton's second law for each one of the two masses. So I'm going to look at m1 over here and then m2 over here. Okay. Let's see how we can actually solve these guys together. So in the first case, what I know is, again, that my acceleration is going down the direction of the plane. So what I'm going to do in this case then is I'm going to use that down the direction of the plane is my positive x direction. Now, again, as I mentioned in the previous video, the reason I want to take the positive x in the same direction as the acceleration is, I'm going to go back to Newton's second law. Since my acceleration is a vector, I can't forget about the negative sign that would come in from account if I chose it in the opposite direction as my positive x-axis. So in this case, I want to choose it in the same direction, so I don't have to forget about that negative sign. Here then, this is then going to be my y direction, which means this is also my y direction, which means by alternate interior angles, this is my angle of theta. Now, in this case, since all I care about is the acceleration, and there's no acceleration in the y direction, let's only look at some of the forces in the x direction. So again, the way that this works is, again, the first thing I'm going to do is ask myself a yes or no question. I'm going to say, is m1 accelerating? In this case, the answer is yes in the x direction. So here, the sum of the forces then on m1 is then going to be equal to m1a. Now, one other thing I'll point out here is make sure you pay attention to your subscripts. Because as you'll notice when we solve this problem, what will happen is I'm going to get two masses, where one is going to be m1, the other is going to be m2. If I don't put my subscripts on these things, I'm going to start randomly canceling masses that aren't the same, and I'm going to get the wrong answer at the end of the day. So make sure we pay attention to these subscripts, otherwise we're going to get all the wrong answers. Great. So in this case, Newton's second law. So now the left-hand side, again, is the complicated geometrical expression of all the forces acting in that direction. So looking at my picture, what I see then is I have the tension. So all my tension here is acting in the x direction. I'm going to write this then as my tension. In this case, it's pointing in the positive x direction, so that makes that guy positive. The other force I have is then this portion here of the weight also pointing in the x direction. Okay, so this is my projection of it along the x direction. Now, in this case, it's also positive because it's pointing again in the direction of the positive x direction. And in this case, this is the opposite side according to that angle, and opposite side is just simply going to be the sine portion. So this is going to be then m1g sine of theta is all then equal to m1a. So this is then the sum of the forces in my x direction. So from here, what this says then is I can find the acceleration if I know first mass m1, and let's say I do, that's given a number. If I know the angle of the plane, and let's say I do, that's given as a number like 30 degrees. If I know g, which of course I always know g, if I know m1, which I do, and if I know the tension. Of course, at this stage, I don't know what the tension is. So I got to figure out where does the tension actually come from, and that's where the second picture is going to come from. So in the second picture, we can then write that's what. In this case, I'm going to take my positive y direction to be in the direction of the acceleration, which since it's accelerating downward, I'm going to take positive y to be downward. So in this case, I can then say the sum of the forces in my y direction are equal to, is it accelerating? Yes, good. So m2a. So here, again, I'm going to look at what forces do I have acting in my y direction. Well, here I have the weight, and I have all the weight, and it's pointing in the positive y direction. So in this case, I'm going to get an m2g. Other than that, I have my tension force. So here's my tension force. So my tension is all of it, but it's pointing in the opposite direction of positive y. So I get a negative sign, and that's all then equal to m2a. Good. So let's look at this one. So this one says I could find the acceleration if I know m2, which I'm presuming I do, if I know g, which I do, and if I know the tension. Again, I don't know the tension. But what I do notice is that, again, by Newton's third law, the tension on the m1 is exactly equal to the tension on m2. So I can use the fact that they're the same and then solve this for the acceleration. Now, I have multiple different ways I can do this. One way I could do it is I could use one of these two to solve for the tension, plug it into the other one, and then solve it that way. Whatever way you want to do with the system of equations, it's completely up to you. The other thing you notice is that now we've already taken all of the directional properties into account when it comes to the vector portions, which means that these are now just algebraic expressions. which means what happens if I take the equation for M1 and I take the equation for M2 and I add them together? Well, in this case, I can see that I have a t on the left-hand equation and I have a negative t on the right equation, which means if I add those two equations, let's call that equation 1 and equation 2, then in this case, the t's are simply going to cancel. So what I can notice then is since they're now algebraic expressions, if I take equation 1 plus equation 2, my two tensions are going to cancel. So let's go ahead and do that. So equation 1, so it gives me a t plus m1g sine of theta is equal to m1a. And I'm going to add that then to m2g minus t is then equal to m2a. So if I add these together, again, what's going to happen now is my two tensions are going to cancel. And I'm going to be left with what? M2g plus m1g sine of theta is then equal to m1 plus m2 times a. On the right-hand side, I've simply just factored out a. Okay? Now, this is something I brought up earlier. Again, be careful here because, again, notice the subscripts on the masses. I have M1s and M2s floating around, where if I only called them M's, not using the fact that they could be two different masses, I would now just be canceling stuff. And ultimately, that wouldn't be good. So I would end up again with the wrong answer. So from here, I would simply solve for the acceleration. So this tells me my acceleration then is going to be, let's factor out a g. So I'm going to get an m2 plus m1 sine of theta all divided by m1 plus m2. This is then my acceleration. Now, in this case, first note that since the acceleration is equal to a positive, that means the direction of the acceleration that I found was correct, because if I got a negative sign, all that means is that the direction of the acceleration would be in the opposite direction. But here, since I chose that M1 was going down the plane and M2 was going under acceleration downward, the fact that the acceleration is positive tells me that I chose the right directions. The other thing is, let's make sure that it's dimensionally correct. So as we talked about before, we want to make sure that our equations have the right units to them. Now the left-hand side has units of acceleration. That means the right-hand side also has to have units of acceleration. So in this case, if I look at it, what I can see then is that g has units of acceleration. And then that means that the portion, which is now the derivative, or not the derivative, the quotient here has to be a dimensionless quantity. And we can see that's actually true. Here I have mass plus mass times sine, but again, sine we know is a dimensionless quantity, so that's mass plus mass divided by mass plus mass, which is dimensionless. So ultimately, this thing has exactly the correct units to it. So this thing makes sense. So good. So just kind of recap. So again, whenever I have connected objects, Newton's third law ultimately just tells me that the acceleration of the two objects has to be the same. For now, what that means then is if they're connected via something like a string, something like this, where again I have one object connected here, and then I have a pulley and this other object that's connected down here, tells me that the tension here must be exactly the same as the tension here. But again, that's because my pulley here is massless and frictionless. Once that thing becomes no longer massless and frictionless, these two tensions won't be the same anymore, but it will still be true that the acceleration of this object here going down this direction and my p's here, this mass here, or this object, will have exactly the same accelerations. So ultimately, we can think about that's what the third law tells us. The third law simply tells us that these two have to have exactly the same acceleration. Or if I had three objects connected, they would have exactly the same acceleration. Now, but again, when I write out Newton's second law, I can only write out Newton's second law for one object at a time. I can't write an expression that has both of the two objects in it simultaneously. So when I'm writing out, in this case, say M1 here, when I'm looking at M1, I'm only writing out the forces which are acting on M1. When I'm writing out for M2, I'm only looking at the forces which are acting at M2. I'm never making direct reference to the other mass because the other mass is automatically taken into account once I realize the fact that the tension here is exactly the same as the tension here. So again, the tension is typically going to act as an intermediate then between the two masses saying that, hey, I exist, and the reason you're being pulled is because I'm pulling on this, which is then pulling on you. But again, if we think about it, M1 doesn't care what's pulling on it. All M1 cares is that it feels the tension force, which is coming from somewhere. It just feels that force. It doesn't care what's actually causing that force. It doesn't care if it's the mass M2 falling or if it's me pulling on it or If it's connected to a belt, it doesn't matter. M1 doesn't care. Only M1 cares about is that it feels a tension. M2 is going to care only that it feels a tension, which is causing it to not fall under free fall. So in this case, it won't feel an acceleration equal to G because of that tension, which is pulling up on it, which is keeping it from undergoing free fall. This is all M2 cares about. It feels a tension. Doesn't care where the tension is coming from. But again, the information that M1 will gain about M2 will come via the tension and vice versa. So again, when it comes to connected objects, we have to be a little bit careful. We can only take one particular object at a time. Now, the other thing to point out here real quick before I end this particular video is that notice here, I'm using two different coordinate systems for the two different objects. Now, this goes back to what Hannah asked in my second class, in the fact that if I have different objects, I can have different coordinate systems. I don't have to have the same coordinate system. Or in that case, she was actually asking if I had different stages of a motion, I could use different coordinate systems. And again, the reason for that is that the magnitude of the acceleration is constant and no matter what coordinate system I use. So as long as I'm self-consistent with the actual mass itself and its coordinate system of choice, I'm not going to run into any problems. So what basically I want to do is I always want to choose the simplest coordinate system, which is going to be able to let me to solve for the forces and the acceleration on a particular mass at a time. So this is Newton's third law. So again, Newton's third law is typically going to be taken into account when I have connected objects or two objects which are pushing against each other. And it just simply says that whenever I have two or more objects interacting with each other, each one of those objects will then feel a force due to the original one pushing on it. So in that case, if I have object one pushing onto object one will feel a force by object two because it can't move through object two. Simultaneously, object two will feel a force by object one because object one is trying to push through it. But the magnitude of the forces on each one are exactly the same and they are completely in opposite directions. So this is Newton's third law. But again, as far as we're concerned, all that means then is that the acceleration of each one of the objects has to be exactly the same until they come apart. Once they're no longer connected, then they can feel different accelerations, which will happen. So that's Newton's third law. So in the next video, we're going to start looking at one more force that we're going to see a lot throughout the semester, which is what's called the friction force. So,